For nearly 6,000 exoplanets discovered by human beings, not one of them looked like this. Every single planet found beyond our solar system before this moment was detected the same indirect way. Watching a star's light flicker as something unseen passed in front of it, or measuring a tiny wobble in a star's position caused by the gravity of something we couldn't actually see. Astronomers had gotten remarkably good at finding planets they could never actually look at directly. And then, in the debris disk of a young star drifting through the constellation Antlia, roughly 111 light years from where you're sitting right now, something different happened. A telescope pointed its instruments at that star, blocked out its light with a device precise enough to be described as one of the hardest engineering problems in modern astronomy, and captured something no one had ever captured before. Not a shadow, not a wobble, not an inference, an actual image, a faint point of infrared light, sitting exactly where theory predicted a hidden planet should be, carved into a ring of dust and rock by something with real mass and real gravity. This is the story of TWA-7b, the first planet the James Webb Space Telescope has ever found by simply looking at it, and why astronomers are calling it the opening move in an entirely new chapter of how we search for other worlds. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why capturing a direct image of an exoplanet is such a genuinely difficult problem, you first have to understand the basic physics working against you every single time you try. Stars are extraordinarily bright. Planets, by comparison, are extraordinarily faint, reflecting or radiating only a tiny fraction of the light their host star produces. Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research, and the lead author of the study that would eventually confirm this discovery, has described the challenge in the simplest possible terms. The star is bright, and the planet is very faint. From Earth's vantage point, a planet sitting anywhere near its host star gets almost completely drowned out by the star's glare, the same way you'd struggle to see a firefly sitting directly next to a lighthouse. This is precisely why, out of the nearly 6,000 confirmed exoplanets cataloged by astronomers as of 2025, the overwhelming majority were found using indirect methods. The transit method watches for the tiny, periodic dimming that happens when a planet passes directly in front of its star from our line of sight. The radial velocity method measures the subtle gravitational tug a planet exerts on its star, causing the star itself to wobble slightly back and forth. Both techniques are powerful, and both have found thousands of worlds. But neither one lets you actually see the planet itself. You're inferring its existence from the effect it has on something else. Direct imaging, actually capturing photons of light that came from the planet, or in this case, from the planet's own heat, is a fundamentally different and vastly more difficult achievement. And before this discovery, the James Webb Space Telescope, despite everything else it had accomplished since becoming operational in 2022, had never managed to find a brand new planet this way. The tool that finally made it possible is called a coronagraph, and it's worth taking a moment to understand what an extraordinary piece of engineering it actually is. A coronagraph is essentially a precision light blocking mask, built to suppress the overwhelming glare of a star so that much fainter objects sitting nearby, planets, debris disks, faint companion stars, can actually be detected. The specific coronagraph used in this discovery was installed on Webb's mid-infrared instrument, known as MIRI, and it was designed and built in France. A critical piece of hardware contributed to Webb's overall observatory design specifically to enable exactly this kind of observation. Even with that instrument in place, actually pulling off the detection required an enormous amount of careful image processing after the raw data came back, subtracting out the residual glare that still managed to leak past the coronagraph's blocking mask, isolating the faint infrared signal that remained. When that processing was finished, what emerged in the data was a clear, distinct source of infrared light sitting near the young star TWA-7, separate from the star itself, exactly where a hidden planet's heat signature would be expected to appear. Now, here's where the story becomes something closer to genuine detective work, because the researchers didn't just get lucky pointing a telescope at a random star and stumbling onto a planet. They had a specific, informed reason to suspect something was hiding there in the first place. TWA-7 is a young star, roughly 6.5 million years old, essentially a cosmic infant compared to our own 4.5 billion-year-old sun, and like many young stars, it's surrounded by a debris disk, a wide, flattened ring of leftover dust, ice, and rocky material left over from the star's formation, the same basic kind of material that, over millions of years, gradually clumps together to build planets. When astronomers studied the structure of TWA-7's debris disk using ground-based observations from the European Southern Observatory's Very Large Telescope in Chile, they noticed something telling. The disk wasn't a smooth, uniform ring. It showed distinct structure, including a narrow, relatively empty gap carved into the material at a specific distance from the star. gaps like that don't typically appear on their own. The leading explanation, based on decades of studying how planetary systems form, is that something with real gravitational pull, a planet, is orbiting inside that gap. Its gravity sweeping the surrounding dust and debris clear as it moves, carving the disk the same way a plow carves a furrow through a field. So when Lagrange and her team turned Webb's coronagraph toward TWA7, they weren't searching blindly. They were looking at a specific location, predicted in advance by the physical structure of the disk itself, and there, exactly where the math said something should be, Webb found it. The object, designated TWA7b, turned out to have a mass roughly similar to Saturn, somewhere in the range of 95 times the mass of Earth, based on the team's analysis of its brightness and estimated temperature. That number matters enormously, and here's why. Every planet previously discovered through direct imaging techniques going back to the earliest successful direct imaging detections in the mid-2000s has been significantly more massive than this. Direct imaging has historically been a technique best suited to finding the biggest, hottest, most luminous planets, ones several times more massive than Jupiter, sitting far enough from their stars that the glare problem becomes slightly more manageable. TWA7b, at roughly a third of Jupiter's mass, is the lightest planet ever successfully captured through direct imaging in the entire history of the technique. NASA and the research team have been explicit about why that specific milestone matters so much. It's not just a new planet. It's proof that our instruments have crossed a genuine threshold in sensitivity, opening the door to directly imaging progressively smaller, cooler, less massive worlds than anything direct imaging could reliably detect before. Worlds that inch closer, generation by generation, to the size and mass range of rocky planets like our own. It's worth pausing here to be precise about the current state of the science, because good reporting on this discovery has to include some honest caveats, and that honesty is part of what makes the story credible rather than exaggerated. As of the original publication in Nature in June 2025, the research team described TWA7b as the telescope's likely first direct imaging discovery, with the object's characteristics, its position relative to the disk gap, its estimated mass, its temperature, all strongly consistent with a genuine planet rather than a background object like a distant galaxy or foreground contaminant like an asteroid happening to drift through the field of view at the wrong moment. The team ran the statistics on exactly that possibility, calculating that the odds of this signal being an unrelated background object were extremely low, but confirming a discovery like this with full certainty typically requires additional follow-up observations over time, tracking the object's motion to verify it's genuinely gravitationally bound to TWA7 and orbiting it the way a real planet would, rather than simply sitting in the same patch of sky by coincidence. That confirmation process has continued in the time since the initial announcement, with astronomers treating TWA7b as one of the most promising and best supported direct imaging candidates ever found, even as the broader scientific community continues refining and verifying the details. What makes this discovery resonate beyond just the specific planet itself is what it represents for the future of exoplanet science as a whole. Since becoming fully operational in 2022, the James Webb Space Telescope had already reshaped how scientists study planets beyond our solar system, but almost entirely by characterizing worlds we already knew existed, using its extraordinary sensitivity to analyze the atmospheres of previously discovered exoplanets, identifying specific molecules, mapping rough temperature patterns, refining our understanding of planets found years earlier through transit or radial velocity methods. TWA7b represented something categorically different. The first time Webb had gone looking and actually found something nobody had ever detected by any method before, using nothing but the light, or in this case the heat, that the planet itself was giving off. Sasha Hinckley, an astronomer at the University of Exeter who has worked extensively with Webb's imaging capabilities, has described this moment as a genuine turning point, noting that reaching into the mass range of a TWA7b required imaging performance that pushes right up against the theoretical limits of what the observatory's optics were designed to achieve. In plain terms, Webb wasn't just lucky here. It performed right at the edge of its engineering capability, and it worked. And there's a deeper reason astronomers care so much about proving this technique works reliably at these lower masses, one that connects directly to the biggest unanswered question in the entire field of exoplanet science. Every method we currently use to search for potentially habitable, Earth-like worlds around other stars has real limitations. The transit method requires a planet's orbit to be perfectly aligned so it passes directly in front of its star from our exact vantage point, a geometric coincidence that rules out the vast majority of planetary systems in the galaxy simply because their orbital planes don't happen to line up with Earth's line of sight. The radial velocity method struggles increasingly the smaller and lighter a planet gets, since the gravitational wobble a small Earth-sized world induces in its star is extraordinarily subtle, at the very edge of what current instruments can reliably measure. Direct imaging sidesteps both of those limitations in theory, but only if the technology exists to actually detect something as faint as a small, cool, rocky planet sitting relatively close to the overwhelming glare of its star. TWA-7b, sitting at roughly a third of Jupiter's mass, is still a long way from an Earth-sized world in terms of raw mass, but it represents real demonstrated progress down that exact ladder. Proof that each generation of instruments and processing techniques is inching the boundary of what's directly detectable further toward the smaller, cooler, rockier worlds that matter most in the search for potentially habitable environments beyond our own solar system. There's also something worth sitting with about the method itself, beyond the specific numbers. Every other technique for finding exoplanets tells you about a planet's existence through absence or disturbance, a dimming of starlight, a wobble in a star's position, a gap carved into a debris disk. Direct imaging is different in a way that's almost philosophical. It's the difference between deducing that someone walked through a room because you found their footprints and actually watching them walk through the door. TWA-7b is a planet we can point to, an actual location in an actual image, however faint that point of light might be, that we know is a physical object and not a mathematical inference. As instruments continue to improve, both aboard Webb and with future observatories currently in development, that ability to simply look at another world rather than deduce its presence indirectly is expected to become one of the most important tools available for eventually finding and studying in real detail an Earth-like planet orbiting another star. For now, TWA-7b remains a young Saturn mass world, orbiting a 6.5 million-year-old star, roughly 111 light-years from Earth, sitting inside a debris disk that first tipped astronomers off to its existence years before the telescope capable of actually confirming it had even been built. It is, by every measure available to us right now, the lightest planet ever captured through direct imaging, and the first new world the James Webb Space Telescope has ever found simply by looking. Astronomers are already using the techniques refined in this discovery to search other young, disk-bearing stars for similar hidden worlds, and every successful detection at this mass range makes the next, slightly smaller discovery a little more achievable than it was before. If this kind of story is what you come here for, one built on real, verified science rather than exaggeration, hit subscribe and turn on notifications, because there's a lot more of the universe left to actually see. Drop a comment telling me what you think the next generation of telescopes will find, and share this with someone who still thinks we've never actually seen another planet up close.